Picture this: a force in the cosmos so overwhelming it bends the very fabric of reality, where magnetic fields reach strengths beyond human comprehension. These aren't just ordinary forces, they're cosmic monsters capable of shredding atoms, warping space-time, and powering some of the most extreme phenomena in the universe. Welcome to the hidden world of extreme magnetic fields, a realm where neutron stars become cosmic lighthouses, black holes twist the laws of physics, and entire galaxies hum with invisible energy. Today, we're diving into 30 astonishing facts about these magnetic powerhouses, uncovering how they shape the universe in ways that defy imagination. Think about the strongest magnet you've ever encountered, maybe a refrigerator magnet or the ones used in advanced medical machines. Now multiply that power by 100 trillion, and you're still only scratching the surface of what exists out there. In the depths of space, magnetic fields reach intensities so fierce they can accelerate particles to nearly the speed of light, heat matter to millions of degrees, and even influence the birth and death of stars. These forces aren't just background actors in the cosmic drama, they're the architects of some of the most violent and beautiful events in the universe. Why should you care? Because these magnetic extremes hold the keys to understanding the universe's biggest mysteries. They dictate how black holes feed, how stars explode, and even how life itself might find a foothold in the most unlikely places. From the mind-bending magnetism of magnetars to the colossal fields surrounding supermassive black holes, every fact we uncover brings us closer to solving the puzzles of the cosmos. So buckle up, because what you're about to discover isn't just science. It's a journey into the heart of the universe's most electrifying secrets. If Earth's magnetic field feels strong enough to guide compass needles across continents, imagine a force so intense it could strip the atoms from your body from thousands of miles away. That's the reality of magnetars, the universe's ultimate cosmic magnets. These aren't just any neutron stars, they're the remnants of supergiant stars that went out with a bang, collapsing into cores so dense a single teaspoon of their material would weigh billions of tons. But what truly sets them apart is their magnetism. With fields reaching up to a quadrillion times stronger than Earth's, they're the most magnetically charged objects known to exist. Their creation is as violent as their nature. When a massive star exhausts its fuel and explodes in a supernova, its core doesn't just fade away, it collapses inward at unimaginable speeds. If the conditions are just right, the spinning core amps up its magnetic field to unimaginable levels, birthing a magnetar, and these cosmic powerhouses don't sit quietly. Their crusts, under immense magnetic stress, occasionally crack in catastrophic events called starquakes. Think of it like an earthquake, but on a scale that warps the laws of physics. When a magnetar's crust shifts, it unleashes gamma-ray flares so powerful they can outshine entire galaxies for a fraction of a second. In 2004, a magnetar 50,000 light-years away released a burst so intense it temporarily ionized Earth's upper atmosphere despite being halfway across the Milky Way. That's the kind of raw, universe-shaping power we're dealing with. These flares are so energetic they can distort the very fabric of space-time around them, creating ripples in reality itself. Yet, for all their destructive potential, magnetars also serve as cosmic laboratories. Their extreme conditions let scientists test theories about matter under pressures and magnetic forces impossible to replicate on Earth. They're natural particle accelerators, flinging charged particles at near-light speeds and generating X-rays that help us map the invisible magnetic architecture of the cosmos. Without these terrifying yet fascinating objects, we'd understand far less about how magnetic fields shape the universe, from the smallest atoms to the largest galactic structures. What's even more mind-bending, some magnetars slow down over time as their magnetic fields sap their rotational energy. But occasionally, they speed up again in sudden, unexplained glitches, hints that beneath their deadly exteriors there's still much we don't understand. These unpredictable behaviors keep astronomers on their toes, reminding us that even in a universe full of extremes, magnetars stand in a league of their own. If magnetars are the superheroes of cosmic magnetism, then SGR 180620 is their undisputed champion. This record-breaking magnetar doesn't just have an intimidating name, it holds the title for the strongest magnetic field ever measured in the known universe. Clocking in at around a quadrillion times stronger than Earth's magnetic shield, its pull is so intense it could distort the electron clouds of atoms from thousands of miles away. But what truly cemented its place in astrophysical lore was the cataclysmic tantrum it threw back in 2004, an outburst that rewrote our understanding of stellar violence. On December 27th of that year, SGR 180620 unleashed a gamma-ray flare so powerful it briefly outshone the full moon. Let that sink in. A single stellar remnant, located 50,000 light-years away in the distant constellation of Sagittarius, blasted enough energy in a tenth of a second to outshine every star in our galaxy combined. The flare was so intense it temporarily scrambled Earth's ionosphere, the layer of our atmosphere responsible for reflecting radio signals. Satellites detected the disturbance, and for a few surreal moments, Earth itself felt the ripple of a cosmic event halfway across the Milky Way. Scientists later calculated that the energy released in that split second exceeded the total output of our Sun over 150,000 years. To put it another way, imagine compressing the entire lifetime energy of 150,000 suns into a blink, and then hurling it across space with pinpoint accuracy. That's the scale of destruction we're talking about. What caused this apocalyptic burst? A starquake, a fracture in the magnetar's ultra-dense crust, buckling under the strain of its own magnetic field. When the crust finally snapped, it unleashed a shockwave of charged particles and radiation, twisting space-time itself in the process. But here's the twist: SGR 180620 wasn't done. In the years following its record-breaking flare, it continued to spit out smaller bursts, proving magnetars aren't one-hit wonders. They're erratic, restless monsters, simmering with pent-up energy until their next explosive episode. This unpredictability makes them both a nightmare and a goldmine for astronomers. Nightmare because their outbursts can blind our detectors without warning. Goldmine because each eruption gives us a rare glimpse into physics beyond anything we could recreate on Earth. And yet, for all its destructive potential, this magnetar also serves as a cosmic beacon. Its extreme magnetism bends light in ways that let scientists probe the very nature of space-time. Some theories even suggest these ultramagnetic fields could be the key to unlocking mysteries like dark matter or quantum gravity. So while SGR 180620 might sound like a celestial menace, it's also one of the universe's greatest teachers, reminding us that sometimes the most violent forces in nature also hold the deepest secrets. While magnetars showcase the raw power of isolated cosmic magnets, supermassive black holes take magnetic influence to an entirely different scale, where these fields don't just warp atoms but shape entire galaxies. At the heart of our Milky Way, Sagittarius, a star, holds court as a gravitational titan. But what often gets overlooked is the colossal magnetic dance happening just beyond its event horizon. Unlike magnetars, where magnetism comes from ultra-dense spinning cores, black holes generate their fields through chaos, specifically the superheated whirlpool of matter known as the accretion disk. Picture an invisible hurricane with winds made of plasma, twisting at nearly the speed of light as it spirals toward oblivion. The friction of particles colliding in this death spiral doesn't just produce blinding radiation, it also ionizes gas into a sea of charged particles, creating electric currents powerful enough to generate magnetic fields billions of times stronger than Earth. What's astonishing is how these fields organize themselves. Thanks to the Event Horizon Telescope's landmark images, we've seen firsthand how these magnetic lines aren't random. They form elegant spiral patterns like cosmic fingerprints swirling around the black hole's shadow. These aren't just pretty visuals. The spiral structure acts like a cosmic particle accelerator, channeling jets of energy so powerful they can stretch for thousands of light years. Some theories suggest these magnetic fields might even explain why certain black holes fired jets at near light speed like cosmic railguns launching matter across intergalactic space. Without these magnetic highways, galaxies wouldn't evolve as they do because those jets regulate star formation by heating surrounding gas clouds, preventing them from collapsing into new stars too quickly. But here's where it gets stranger. Recent observations hint that Sagittarius, a star's magnetic fields, might flip polarity, switching north and south in turbulent cycles. Imagine Earth's magnetic poles reversing, but compressed into a time frame of hours instead of millennia. This could explain why some black holes flicker unpredictably in X-ray emissions, as their magnetic chaos reroutes the flow of doomed matter at the last second. The takeaway: black holes aren't just gravity wells, they're electromagnetic engines, sculpting their surroundings with forces we're only beginning to map. And with each new observation, we're uncovering how these invisible fields dictate some of the most spectacular acts in the cosmic theater. Pulsars take the raw power of magnetars and channel it into something even more extraordinary: precision. Imagine a celestial lighthouse spinning at dizzying speeds, sweeping beams of radiation across the cosmos with clockwork regularity. These rapidly rotating neutron stars aren't just remnants of supernova. They're cosmic metronomes, their rhythmic pulses so reliable they rival atomic clocks here on Earth. But what gives pulsars their signature flashes isn't just speed. It's the interplay between their blistering rotation and magnetic fields strong enough to bend light itself. Take the Crab pulsar, one of the most studied objects in the sky. Born from a supernova observed in 1054, this stellar corpse spins 30 times every second, hurling beams of radio waves and gamma rays into space like a hyperactive cosmic strobe light. Its secret: a magnetic field measuring 30 terahertz, roughly a trillion times stronger than Earth's. This isn't just a static force, it's a dynamic engine, accelerating particles to near-light speeds along the pulsar's magnetic poles. As these charged particles spiral along the field lines, they emit radiation in narrow cones, creating the lighthouse effect we observe from afar. What's astonishing is how these beams stay so focused. The Crab pulsar's magnetic field acts like a cosmic collimator, squeezing radiation into tight jets that sweep past Earth with each rotation. When one of these beams aligns with our telescopes, we detect a pulse, a flash so regular you could set your watch by it. But miss that alignment by even a fraction of a degree, and the pulsar becomes invisible, vanishing like a spotlight turning away. This razor-thin margin is why discovering pulsars requires both precision and patience, and why their pulses feel like deliberate signals from the universe. Yet pulsars aren't just celestial timekeepers. Their extreme environments make them natural laboratories for testing physics. The Crab pulsar's magnetic field, for instance, is so intense it can generate antimatter in the form of positrons, which annihilate upon contact with electrons, releasing bursts of gamma rays. These processes are so energetic they've been detected lighting up the surrounding Crab Nebula, painting a portrait of how magnetic fields can sculpt entire stellar graveyards. And here's the twist: some pulsars, known as millisecond pulsars, spin hundreds of times per second. Their magnetic field slightly weaker, but their precision even more astonishing. These speed demons challenge our understanding of how neutron stars evolve, suggesting they might steal matter from companion stars to rev up their rotation. Whether slow or fast, pulsars remind us that in the universe's most extreme environments, magnetism doesn't just distort reality, it orchestrates it. But what happens when a neutron star isn't alone in the void? Enter binary systems, cosmic duos where gravitational theft turns already extreme magnetic forces into something even more spectacular. Take Hercules X1, a neutron star locked in a deadly dance with a companion star. Unlike lone magnetars that rely on their own spin for power, objects like Hercules X1 become magnetic vampires, siphoning gas from their neighbors to fuel eruptions that defy logic. Every orbit, this neutron star's gravity rips matter away from its companion, funneling it into an accretion disk swirling at relativistic speeds. As this stolen plasma spirals inward, something extraordinary happens. The sheer violence of the collision amplifies the star's magnetic field to levels that make even pulsars look tame. The infalling matter doesn't just crash onto the surface, it gets superheated to millions of degrees, ionizing into a sea of charged particles that twist and stretch the existing magnetic lines. This churning dynamo effect creates localized magnetic hotspots, regions where the field strength spikes unpredictably, launching bursts of X-rays so intense they've been detected across interstellar space. What makes systems like Hercules X1 truly bizarre is their flickering behavior. Unlike the steady pulses of isolated neutron stars, these binary thieves stutter. Their X-ray emissions vanish for hours, then flare back to life with explosive intensity, like a cosmic strobe light with a faulty switch. Astronomers believe this happens when the magnetic field grows so strong it temporarily pushes the accretion disk away, starving the neutron star until gravity inevitably wins and the feast resumes. This push and pull creates a feedback loop of destruction where magnetism and gravity battle for dominance in real time. Yet these chaotic systems aren't just destructive, they're also cosmic alchemists. The magnetic maelstrom in Hercules X1's accretion disk smashes atoms together with such force that it forges heavy elements like gold and platinum materials that eventually get flung into space during particularly violent outbursts. Without these magnetic thieves, the universe might lack the very elements that make up our jewelry and electronics, perhaps the most unsettling revelation. Hercules X1's magnetic field isn't static, it's growing. Each stolen meal from its companion adds energy to the system, ratcheting up the magnetic tension like a coiled spring. One day, this buildup could trigger a magnetar-level eruption, proving that in the cosmos, even theft can have catastrophic consequences. Earth's magnetic field is like a whisper compared to the cosmic screams of a magnetar. Our planet's protective shield measures a modest 0.5 Gauss, just strong enough to guide a compass needle or deflect solar winds. But step into the realm of a magnetar, and you're dealing with fields exceeding 10 to the 15th power Gauss. That's a 1 followed by 15 zeros, a number so vast it defies everyday comparison. If Earth's magnetism were the hum of a refrigerator, a magnetar's would be the deafening roar of a million jet engines. To grasp this difference physically, imagine holding a credit card near the most powerful lab magnet ever built. It might erase the strip from a few inches away. Now picture that same card floating in space, halfway between Earth and the Moon, roughly 120,000 miles out. A magnetar's field could still scramble its data instantaneously from that impossible distance. That's not just strength, that's magnetism warping the very rules of physics. What makes this gap even more astonishing is how these fields behave. Earth's magnetism is stable, a gentle guardian shielding us from cosmic radiation. But a magnetar's field is a violent, twisting force. It doesn't just bend charged particles, it stretches atoms into needle-thin shapes, warping electron orbits until matter itself behaves like putty under its grip. If you somehow survived being near one, your body's atoms would realign like iron filings near a toy magnet, except on a scale where chemistry itself breaks down. Yet these extremes aren't just cosmic curiosities. They're reminders of how diverse magnetic environments shape the universe. Earth's field nurtures life by deflecting deadly radiation. A magnetar's field, it forges new physics in its crucible, challenging everything we know about matter under pressure. Both are magnetic, but where one cradles, the other obliterates, a duality proving that in space, strength isn't just measured in numbers, but in the ability to redefine reality itself. Deep in the cosmic nurseries where stars are born, magnetic fields act as invisible sculptors, shaping chaos into order. Take the Orion Nebula, one of the most active stellar factories in our galaxy. At first glance, it appears as a swirling storm of gas and dust, but hidden within that turbulence are thread-like filaments, perfectly aligned like strokes of a cosmic brush. These delicate structures aren't random. They're the handiwork of magnetic fields weaving through the nebula's molecular clouds, guiding the collapse of star-forming material with meticulous precision. Without these forces, star birth would be a catastrophic free-for-all. Gravity alone would cause gas clouds to crumple inward too quickly, fragmenting into unstable clumps. But magnetism changes the game. As particles in these clouds become ionized, they latch onto magnetic field lines, creating a sort of cosmic scaffolding that slows the collapse. Imagine trying to pour sand through a sieve. The magnetic fields act like that sieve, regulating how fast matter can gather toward the center. This controlled descent allows protostars to form more smoothly, with rotating disks that eventually give rise to planets. The Orion Nebula's famous pillars of creation offer a stunning example. Those towering columns of dust aren't just passive structures, they're cradles of star formation, their shapes molded by magnetic pressure resisting gravity's pull. Spectroscopy reveals these filaments are threaded with magnetic fields strong enough to channel ionized gas along their lengths, like water flowing through invisible pipes. In some regions, the fields are so organized they create shock fronts, where incoming material slams into ordered magnetic barriers, sparking bursts of new star formation. Yet magnetism's role doesn't end there. These fields also determine the size of stars that emerge. In regions where magnetic support is strong, only the densest pockets of gas can overcome the resistance, leading to fewer but more massive stars. Where fields are weaker, smaller stars form in abundance. This delicate balance explains why some nebulae glitter with brilliant blue giants while others teem with modest red dwarfs. What's truly remarkable is how these processes echo across scales. The same magnetic forces that shape a single star's birth also influence entire galaxy evolution. Supernova from massive stars, themselves products of magnetically guided collapse, later seed space with heavy elements and turbulent fields, setting the stage for future generations. So the next time you gaze at Orion's sword, remember, those glittering stars owe their existence to an invisible force, quietly conducting the symphony of creation. The sun may seem like a steady, unchanging orb in our sky, but beneath its fiery surface lies a tempest of magnetic chaos that makes Earth's most violent storms look like a breeze. Unlike the rigid fields of magnetars or pulsars, the sun's magnetism is fluid, dynamic, a constantly shifting web of forces that tangles, snaps, and reconnects with explosive consequences. At the heart of this turmoil are sunspots, those dark blemishes on the solar surface that mark where magnetic field lines burst through like frenzied springs. These aren't just cool patches, they're the battlegrounds of a magnetic war where field lines twist until they rupture in cataclysmic flares. Take the solar flare of November 2003, one of the most powerful ever recorded. In just minutes, it unleashed energy equivalent to 1 billion megatons of TNT, roughly 10 million times the yield of every nuclear weapon detonated in human history combined. That single eruption ejected charged particles at nearly the speed of light, triggering radio blackouts across continents and forcing astronauts on the International Space Station to shelter from the radiation onslaught. And yet, this was just a fraction of the sun's potential. The infamous Carrington event of 1859, a solar superstorm, lit up telegraph lines so intensely that operators could send messages without power, while auroras dazzled as far south as Cuba. What powers these eruptions isn't raw heat but magnetic stress. The sun's equator spins faster than its poles, stretching and shearing magnetic field lines like taffy. Over time, this differential rotation winds those lines into knots, storing unimaginable energy. When the tension becomes unbearable, the fields snap, reconnecting in a process that converts magnetic energy into heat and motion, launching flares and coronal mass ejections. The sheer violence of these events warps the solar atmosphere, sometimes hurling plasma loops hundreds of thousands of miles into space. Yet for all their fury, these magnetic tantrums follow an eerie rhythm. Every 11 years, the sun's field flips polarity entirely, with north and south poles swapping places in a cycle that governs the ebb and flow of solar activity. During solar maximum, sunspots proliferate, flares erupt daily, and the sun becomes a cosmic fireworks show. At solar minimum, it calms, but never truly rests. Even in quiet phases, magnetic bubbles the size of planets rise and vanish, a reminder that our star is never truly still. What's often forgotten is how these magnetic dances shape life on Earth. Beyond the auroras and blackouts, the sun's field shields our solar system from galactic cosmic rays, high-energy particles that could otherwise bombard us unchecked. When solar activity wanes, more of these rays slip through, potentially altering cloud formation and even climate patterns. So while the sun's magnetic chaos might seem distant, it's woven into the very fabric of our existence, a reminder that even the most violent forces in space can cradle life in unexpected ways. Jupiter doesn't just have a magnetic field, it wields a monstrous, swirling fortress of radiation that would make even the bravest spacecraft tremble. Clocking in at nearly 20,000 times stronger than Earth's, this gas giant's magnetosphere is the largest structure in our solar system, stretching so far that if it were visible to the naked eye, it would appear larger than the full moon in our sky. But this isn't just about size, it's about sheer, unrelenting power. Jupiter's magnetic dominion is so vast it deflects the solar wind over 5 million miles away, carving a protective bubble that dwarfs the sun itself. At the heart of this magnetic behemoth lies a churning ocean of metallic hydrogen. Deep beneath Jupiter's colorful clouds, pressures reach such extremes that hydrogen, the lightest element, transforms into a liquid metal, swirling with electric currents. This dynamo effect generates a field so intense it creates radiation belts 1,000,000 times more lethal than Earth's Van Allen belts. Charged particles here whip around at nearly the speed of light, forming a donut-shaped zone of destruction so hazardous it's been called the most hostile environment in the solar system. NASA Juno spacecraft learned this the hard way. Designed to endure Jupiter's wrath, the probe still had to take drastic precautions. Its sensitive electronics were encased in a titanium vault, shielding them from radiation doses equivalent to 100 million dental X-rays. Even so, Juno's cameras and instruments occasionally glitched as charged particles punched through its defenses like cosmic bullets. Every orbit became a high-stakes dance, skirting the edge of Jupiter's radiation belts to gather data while avoiding annihilation. What's truly astonishing is how Jupiter's magnetism shapes its surroundings. The radiation belts aren't static. They pulse and flare in response to solar storms, sometimes ejecting material all the way to Saturn's orbit. Auroras the size of entire planets ignite at its poles, fueled by particles spiraling along magnetic field lines. These aren't the gentle green curtains we see on Earth. They're ultraviolet infernos, releasing more energy than all the power humanity generates in a century. Yet Jupiter's magnetic might isn't just destructive. It's also a cosmic shield protecting its moons from the full brunt of solar radiation. Europa, with its subsurface ocean, might owe its potential for life to this magnetic umbrella. Even the volcanic moon Io feels its influence, as Jupiter's field strips away a ton of sulfur dioxide from its eruptions every second, painting a glowing trail along its orbit. Jupiter's magnetosphere is a reminder that in the cosmos, magnetism isn't just a force, it's a sculptor of worlds, a guardian and a tyrant all at once. And as we continue to study its extremes, we're uncovering secrets not just about our solar system, but about the magnetic monsters that might lurk around distant stars. When massive stars reach the end of their lives, they don't always fade quietly. Some leave behind magnetic tombstones so powerful they defy logic. White dwarfs, the dense cores of dead stars, typically cool into oblivion over billions of years. But a rare breed like PG 1031 plus 234 bucks this trend spectacularly, boasting magnetic fields strong enough to make a refrigerator magnet seem like a joke. At 1 billion Gauss, thousands of times stronger than anything on Earth, these so-called fossil fields are relics of their progenitor stars' violent pasts, frozen in time like cosmic fingerprints. How does a stellar corpse retain such incredible magnetism? The answer lies in a quirk of physics called magnetic flux conservation. When a star collapses into a white dwarf, its core compresses to the size of Earth while retaining much of its original mass. Just as an ice skater spins faster by pulling their arms in, the star's magnetic field amplifies as it shrinks, squeezing those invisible lines of force into a tighter, more intense configuration. For most white dwarfs, turbulence during the death throes scrambles these fields into nothingness. But occasionally, as with PG 1031 plus 234, the field survives intact, a snapshot of the star's final moments preserved in magnetic amber. What's eerie is how these fossil fields behave. Unlike the twisting dynamos of pulsars, they're static, unchanging over millions of years. Picture a bar magnet frozen in space, its north and south poles locked in place as the white dwarf slowly cools. This stability lets astronomers use them as cosmic archaeology tools. By measuring the field's strength and orientation, we can reconstruct details about the original star's rotation and internal structure long after its outer layers have blown away. But PG 1031 plus 234 isn't just a relic, it's an outlier. Most magnetic white dwarfs clock in at a mere 100 million Gauss, making this billion Gauss monster a true cosmic anomaly. Some theories suggest it might be the product of two white dwarfs merging, their combined magnetic fields amplifying to ludicrous levels during the collision. Others propose it's the remnant of an ultra-rare, highly magnetic progenitor star, a celestial unicorn that lived and died under extraordinary circumstances. The real surprise, these fossil fields might not be fossils at all. Recent observations hint some magnetic white dwarfs could harbor faint, residual dynamo activity, perhaps from crystallizing cores or slow-moving convection currents. It's a reminder that even in death, stars can cling to traces of their former vitality, defying expectations in ways we're only beginning to understand. Magnetic reconnection might sound like a dry scientific term, but it's one of the most explosive processes in the universe, the cosmic equivalent of a rubber band snapping after being stretched too far. Picture two magnetic field lines taut with tension as they're pushed toward each other by the chaotic motion of plasma. At first, they resist, bending but not breaking. Then, in a fraction of a second, everything changes. The fields suddenly snap, realigning into a new configuration and releasing a burst of energy so intense it can power everything from solar flares to Earth's dazzling auroras. This isn't just a gentle rearrangement, it's a fundamental transformation of energy. The process converts stored magnetic energy into heat and kinetic energy, accelerating particles to nearly the speed of light. On the Sun, these reconnection events trigger X-class solar flares, eruptions so bright they can momentarily outshine the Sun's entire surface. The record-breaking flare of 2003, for instance, unleashed energy equivalent to 1 billion hydrogen bombs, all thanks to magnetic field lines breaking and reconnecting in the solar corona. But the drama doesn't stop there. These explosions often hurl colossal clouds of charged particles into space coronal mass ejections that can barrel toward Earth at millions of miles per hour. When these particles collide with our planet's magnetosphere, they trigger another round of reconnection, this time on our doorstep. Earth's magnetic field lines stretch and snap, funneling solar wind particles down toward the poles. The result, auroras, those shimmering curtains of light that dance across polar skies. Without magnetic reconnection, these celestial light shows wouldn't exist. The sheer efficiency of this process is what baffles scientists. In just seconds, reconnection can release energy that would otherwise take millennia to dissipate. Laboratory experiments struggle to replicate the speeds at which this occurs in space, suggesting there's still much we don't understand about the underlying physics. Some theories propose that turbulence or quantum effects play a role, but the truth is, the universe holds onto some of its magnetic secrets tightly. Perhaps most fascinating is how reconnection shapes entire star systems. Beyond the Sun, it's been spotted in the magnetospheres of planets, the accretion disks of black holes, and even the violent jets of distant quasars. Each event follows the same basic script: field lines breaking, energy exploding outward, but the scale varies wildly. A solar flare might last minutes, while reconnection in a galaxy cluster could unfold over millions of years. Yet for all its destructive potential, magnetic reconnection also creates order. In star-forming regions, it helps regulate the flow of material, preventing chaotic collapse. In Earth's magnetosphere, it redistributes energy, protecting us from the worst of solar storms. It's a reminder that even in the cosmos, destruction and creation are two sides of the same coin, and magnetism is the force that keeps the balance. The Milky Way isn't just a swirl of stars and gas. It's threaded with an invisible skeleton of magnetic force, a vast web of energy that stretches tens of thousands of light years across the galaxy. Unlike the concentrated fury of a magnetar or the orderly beams of a pulsar, this galactic field is subtle but omnipresent, woven into the fabric of interstellar space itself. Scientists have mapped its structure using a clever trick, observing starlight that's been polarized as it passes through clouds of magnetically aligned dust. These cosmic breadcrumbs reveal a field that's neither uniform nor chaotic, but instead forms intricate patterns like the grain in a piece of celestial wood. What's remarkable is how this field, though a million times weaker than Earth's, manages to shape the galaxy's ecosystem. Cosmic rays, high-energy particles racing through space at nearly light speed, are steered by these magnetic lines, their paths bending into spirals as they traverse the galaxy. Without this guidance, these particles would fly unchecked, bombarding planets and interstellar gas with far more intensity. The field acts like a cosmic filter, subtly directing where and how these rays travel, influencing everything from the chemistry of nebulae to the potential habitability of distant worlds. Then there's the dust. Interstellar space isn't empty. It's filled with microscopic grains of carbon and silicate, the raw materials for future stars and planets. The Milky Way's magnetic field aligns these particles like tiny compass needles, causing them to clump together in ways that gravity alone couldn't achieve. This process isn't just academic, it's why we have planets at all. When the solar system formed, magnetized dust grains likely played a crucial role in building the early protoplanetary disk, their alignment helping materials stick together rather than just scattering in the void. But the galaxy's magnetism isn't static. Near supernova remnants and active star-forming regions, turbulent forces twist and amplify the field, creating localized knots of magnetic energy. These hotspots can accelerate particles to outrageous speeds, acting as natural particle colliders on a scale no human machine could replicate. Meanwhile, in the quieter stretches between spiral arms, the field relaxes into smoother, more orderly patterns, shaping the slow dance of gas clouds over millions of years. Perhaps the most mind-bending realization, this galactic field connects to larger cosmic structures. filaments of magnetism might stretch between galaxies, part of a universe-spanning network we're only beginning to detect. So while the Milky Way's field might seem like a quiet backdrop to the drama of stars and black holes, it's actually a silent architect quietly shaping the destiny of everything within its reach. Hot Jupiters turn the concept of planetary magnetism into something straight out of science fiction. Gas giants so close to their stars they're practically melting, yet armed with magnetic shields powerful enough to hold back a hurricane of stellar radiation. These aren't just bloated versions of Jupiter, they're extreme survivors, enduring temperatures that vaporize rock while generating magnetic fields strong enough to warp the very space around them. Take HD 209458b, a hot Jupiter so close to its star it completes an orbit in just 3.5 days. Despite being bombarded by ultraviolet radiation 1,000 times stronger than Earth receives, this planet hasn't been stripped to its core. Why? Because its magnetic field, possibly 10 times stronger than Jupiter's, acts like an invisible force field, deflecting the worst of its star's fury. These magnetic defenses work like cosmic umbrellas. As the stellar wind, a supersonic stream of charged particles, slams into the planet's magnetosphere, it's forced to divert around it, creating a protective bubble known as a bow shock. For hot Jupiters, this shock front can be enormous, stretching dozens of planetary radii into space. Observations of HD 189733b, another scorching giant, revealed its magnetosphere glowing in ultraviolet light as it repelled its star's onslaught, a telltale sign of charged particles spiraling along magnetic field lines. Without this shield, the planet's atmosphere would have evaporated eons ago, leaving behind a barren core. But here's the twist: these magnetic fields might do more than just protect. They could also create dazzling auroras on a scale that dwarfs Earth. Unlike our planet, where auroras are confined to polar regions, a hot Jupiter's entire dayside could light up as stellar particles flood its magnetosphere, igniting global light shows visible from light years away. Some models even suggest these auroras might heat the planet's upper atmosphere to tens of thousands of degrees, puffing it up like a balloon and giving the planet a hazy, distended appearance when viewed through telescopes. Yet mysteries remain. Why do some hot Jupiters seem to retain thick atmospheres while others wither? The answer might lie in the interplay between their magnetic fields and internal heat. Planets with stronger internal convection, think molten metallic hydrogen swirling beneath their clouds, could generate more intense dynamos, reinforcing their magnetic defenses. Others, perhaps older or less massive, might see their fields weaken over time, leaving them vulnerable to their star's relentless erosion. What's fascinating is how these discoveries reshape our search for habitable worlds. If a hot Jupiter's magnetism can preserve its atmosphere against impossible odds, could smaller, rocky exoplanets do the same? It's a tantalizing thought that magnetic fields, often overlooked in the hunt for life, might be the unsung heroes keeping alien skies intact. As we study these extreme worlds, we're not just learning about planetary survival, we're rewriting the rules of what makes a world livable in this brutal, beautiful universe. Long before galaxies or stars existed, when the universe was just a seething cauldron of plasma, magnetic fields might have already been weaving their invisible threads through the newborn cosmos. These primordial fields, dating back nearly 13.8 billion years, aren't just cosmic relics. They could be the very scaffolding upon which modern galactic magnetism was built. While we can't directly observe these ancient forces, subtle clues linger in the afterglow of the Big Bang itself, the cosmic microwave background radiation. Recent analyses of this faint glow suggest something extraordinary: faint, swirling polarization patterns that some scientists believe could be fingerprints of magnetic fields imprinted when the universe was less than a second old. Imagine the scene: an expanding fireball of particles so hot and dense that atoms couldn't even form. In this chaos, quantum fluctuations and phase transitions might have generated weak but pervasive magnetic fields. Unlike today's organized galactic fields, these early versions would have been turbulent, flickering in and out of existence as the universe expanded at a breakneck pace. What's astonishing is that some of these fields might have survived inflation, the universe's explosive growth spurt stretching from microscopic scales to cosmological ones in the blink of an eye. The evidence lies in the way these primordial fields could have subtly twisted the polarization of the cosmic microwave background. In 2016, researchers studying data from the Planck satellite noticed peculiar spiral patterns in the CMB's polarization signatures that don't quite fit standard cosmological models. One tantalizing explanation, the imprint of primordial magnetism, warping the paths of photons as they traveled across the young universe. If confirmed, this would mean magnetic fields aren't just byproducts of stars or galaxies. They predate them, woven into the universe's fabric from its first moments. But how could something so delicate persist for billions of years? The answer lies in the universe's own expansion. While these early fields would have been incredibly weak, billions of times fainter than Earth's, the sheer vastness of space allowed them to endure, stretching and thinning but never fully dissipating. Over time, as gas clumped into galaxies and stars, these seed fields might have been amplified by dynamo effects, like cosmic amplifiers turning a whisper into a roar. The implications are staggering. If these primordial fields exist, they could explain why galaxies so often show large-scale magnetic structures, patterns too vast and organized to have formed solely from local stellar processes. They might even influence how galaxies spin, how cosmic gas collapses, and where stars ignite. It's a humbling thought. The same magnetic whispers from the universe's birth may still be shaping the cosmos today, hidden in plain sight. The crust of a neutron star is unlike anything in our solar system, a super-dense lattice of atomic nuclei squeezed so tightly together they form a crystalline structure harder than diamond. But even this cosmic armor has its limits, especially when subjected to the titanic magnetic forces of a magnetar. Picture a bridge supporting 1,000,000 times its weight. Now imagine that bridge is made of neutron star crust, and the weight is a magnetic field strong enough to distort atoms. Eventually, something has to give. When the strain becomes too much, the crust doesn't just crack, it shatters in violent ruptures known as starquakes. These aren't the slow grinding of tectonic plates, but explosive snap events, where pent-up magnetic energy releases in milliseconds. The energy discharged in a single starquake dwarfs humanity's combined nuclear arsenals by orders of magnitude. In March 1979, scientists detected a gamma-ray burst from a magnetar in the Large Magellanic Cloud that delivered more energy in a fraction of a second than our Sun emits in 1,000 years. The culprit, a crustal rupture no larger than a few hundred meters across. The physics behind these events is as fascinating as it is terrifying. A magnetar's crust is under constant magnetic tension, its atoms stretched into elongated shapes by the field's overwhelming pull. Like compressing a spring, this stores vast amounts of potential energy. But neutron star crust isn't uniform. Tiny imperfections or uneven cooling create weak points where stress concentrates. When one of these zones fails, the entire crust rebounds, sending seismic waves rippling across the surface at near-light speeds. The resulting vibrations twist the star's magnetic field lines violently, accelerating particles to extreme energies and producing bursts of X-rays and gamma rays visible across the galaxy. What's staggering is how localized these explosions are. Unlike supernova that obliterate entire stars, starquakes release energy from a single fracture, proof of how much power is packed into even a sliver of neutron star material. Some models suggest the crust's outermost layers shatter like glass, while deeper regions undergo a strange plastic deformation, flowing like putty before snapping back. This interplay between brittle and ductile behavior creates a uniquely violent release. channeling the energy upward in focused jets rather than a uniform explosion. Yet the aftermath is just as intriguing. The crust doesn't heal smoothly. Magnetic fields rearrange themselves in the quake's wake, sometimes creating new hotspots where charged particles spiral along realigned field lines, glowing in X-rays for months. These afterglows act like cosmic fingerprints, letting astronomers map the star's magnetic geography. And occasionally, the crust settles into an even more unstable configuration, priming the magnetar for another catastrophic rupture. It's a reminder that in the universe's most extreme environments, even solid ground is anything but stable. Just when we thought we had magnetars figured out, the cosmos throws us a curveball, an object that looks like a magnetar but behaves like a cosmic imposter. Meet SGR-0418 plus 5729, the so-called anti-magnetar that shattered decades of assumptions about how these extreme objects evolve. Unlike its ultramagnetic cousins, this neutron star's surface field measures a puny few trillion Gauss, barely worth mentioning by magnetar standards. Yet despite its comparatively weak magnetism, it still produces the same violent X-ray flares and starquakes we'd expect from a full-powered magnetar. It's like finding a candle that somehow burns as bright as the sun. The mystery deepens when you consider how this anomaly challenges textbook magnetar theory. Traditional models insist these stars need outrageously strong surface fields to power their outbursts. Yet SGR-0418 plus 5729 proves something else is at work. The leading explanation: this isn't a young magnetar losing steam, it's an old one wearing a magnetic disguise. Simulations suggest its true power lies hidden beneath the surface, where twisted field lines remain trapped in the star's superfluid core. Picture an iceberg with only a fraction of its mass visible above water. The star's outer crust might appear weakly magnetic, but beneath it churns a reservoir of pent-up energy waiting to erupt. What's fascinating is how this buried magnetism reveals itself. During rare but violent outbursts, seismic shifts in the crust might briefly expose these interior fields, allowing trapped energy to punch through in spectacular flares. It's the cosmic equivalent of a pressure cooker's lid-rattling steam escaping through the weakest point. Some astronomers suspect this could be the fate awaiting all magnetars given enough time. As they age and their crusts thicken, their once dominant surface fields could become frozen in, sinking deeper while leaving only faint traces above. The discovery of these anti-magnetars forces us to rethink how we categorize neutron stars altogether. The line between magnetars and ordinary pulsars might be blurrier than we imagined, with objects shifting between states over billions of years. It's a reminder that even the universe's most extreme phenomena have life cycles, and sometimes their most dramatic chapters unfold when they're playing dead. Earth's magnetic field might seem like an invisible afterthought, but it's the unsung hero keeping life on this planet alive. Without this protective force field, our world would be bombarded by a relentless storm of cosmic rays, high-energy particles hurtling through space at nearly the speed of light. These aren't just harmless space dust, they're atomic bullets capable of shredding DNA, disrupting cellular machinery, and sterilizing the surface of any planet unlucky enough to lack magnetic armor. Think of Earth's magnetosphere as a cosmic umbrella, its curved field lines bending these lethal particles away from us and funneling them harmlessly toward the poles, where they ignite the auroras instead of our atmosphere. But the real magic lies in the details. When solar winds, charged particles streaming from the sun, collide with Earth's magnetic shield, they don't just bounce off. The field captures and redirects them, creating a buffer zone called the magnetopause. This turbulent boundary acts like a shock absorber, dissipating energy that would otherwise fry our satellites and erode our atmosphere over time. Venus, Earth's twin in size, serves as a chilling cautionary tale. Despite its similar composition, it lacks a global magnetic field, and over billions of years, solar winds have stripped away much of its water, leaving behind a hellish wasteland with an atmosphere 90 times thicker than ours, proof that magnetism isn't just a luxury for habitability, it's a necessity. Yet Earth's field does more than deflect. It also preserves the delicate balance of our atmosphere, preventing solar winds from slowly chipping away at the oxygen and nitrogen that make life possible. Mars, with its weak, patchy magnetism, couldn't hold onto its once thick atmosphere, and today it's a barren desert. Even more striking, some studies suggest that during periods when Earth's magnetic field weakened, like the Lashump excursion 41,000 years ago, increased cosmic radiation may have triggered extinctions and forced early humans into protective caves. The implications for finding life beyond Earth are profound. Astronomers hunting for habitable exoplanets now prioritize worlds with strong magnetic fields, knowing that without this invisible shield, even the most Earth-like planet could be a radiation-blasted wasteland. Recent discoveries of rocky exoplanets with potential magnetospheres like Proxima Centauri b ignite excitement because they hint at environments where life might cling on against the cosmic onslaught. Perhaps the most humbling thought, Earth's magnetic field isn't static. It fluctuates, reverses, and even generates localized weak spots like the South Atlantic anomaly, where satellites risk malfunction from increased radiation. Yet despite its imperfections, this shimmering force field has guarded life for billions of years, a silent sentinel standing between us and the void. If that's not a reason to appreciate the invisible forces shaping our existence, nothing is. Quasars don't just shine, they scream across the cosmos with jets of plasma so powerful they dwarf entire galaxies. These aren't ordinary beams of light, they're cosmic particle accelerators stretching millions of light years into intergalactic space, propelled by magnetic fields of almost incomprehensible strength. At the heart of every quasar lies a supermassive black hole, but it's not just gravity doing the work here. The real magic happens in the accretion disk, where spiraling matter generates magnetic fields so twisted they act like celestial slingshots, hurling particles outward at nearly the speed of light. Picture a tornado made of ionized gas spinning at relativistic speeds around a black hole's maw. As charged particles whirl through this chaos, they latch onto magnetic field lines which coil like springs under the strain. When the tension becomes unbearable, the fields snap not once, but continuously flinging particles along the black hole's spin axis in oppositely directed jets. This process, called magnetic reconnection, doesn't just nudge particles forward. It catapults them with such force that they emit blinding radiation across the electromagnetic spectrum, from radio waves to gamma rays. The jet from Quasar 3C273, for example, stretches over 1 million light-years, longer than the span of 20 Milky Ways placed end to end. What's staggering is how efficiently these jets maintain their focus over such colossal distances. Unlike a flashlight beam that scatters, quasar jets stay collimated, piercing through intergalactic space like laser pointers. The secret lies in the magnetic field's self-sustaining structure. As particles spiral along the field lines, they generate additional magnetism through their motion, creating a feedback loop that keeps the jet tightly wound. Some theories suggest these fields even induce a sort of cosmic superconductivity, where resistance vanishes and particles flow without losing energy, a phenomenon we've only glimpsed in labs under extreme conditions. But the true testament to these jets' power lies in their impact. When a quasar jet slams into intergalactic gas, it doesn't just push it aside. It triggers shock waves that heat the surrounding material to millions of degrees, preventing it from cooling and forming new stars. Entire galaxy clusters can be sterilized this way, their gas kept too hot to collapse. In a sense, quasars don't just illuminate the universe, they shape its evolution, using magnetic fields as both engine and sculptor. The most mind-bending part, we're seeing these jets as they were billions of years ago, relics of a younger, more violent universe. Yet their magnetic engines still hold clues about how black holes and galaxies co-evolved. By studying the polarization of light from these jets, astronomers can map their hidden magnetic structures, peeling back layers of cosmic history. It's a reminder that even in the darkest corners of space, magnetism writes the rules and occasionally bends them beyond recognition. Even the most extreme objects in the universe have their off switches, and neutron stars are no exception. Take PSRB 1931+24, a pulsar that behaves like a celestial strobe light, flicking its radio emissions on and off without warning. For days or weeks at a time, its rhythmic pulses vanish completely, leaving astronomers staring at silence where a cosmic metronome should be. This isn't just a temporary glitch, it's evidence of a bizarre phenomenon called the magnetospheric gap, regions around neutron stars where the physics we thought we understood simply breaks down. At the heart of this mystery lies a fundamental question: how can a pulsar's magnetosphere, a structure built on relentless magnetic precision, suddenly develop dead zones? The leading theory points to a delicate balance between two competing forces. Normally, a pulsar's rotation and magnetic field work in tandem to generate a cascade of charged particles above its poles, creating the beams of radiation we detect as pulses. But in pulsars like PSRB 1931+24, something disrupts this process. The magnetosphere may become empty, a void where charged particles vanish faster than they can be replenished. Without these particles to carry currents, the radio beacon flickers out, leaving behind a silent neutron star still spinning invisibly in the dark. What triggers these gaps? One possibility involves strange quantum effects near the pulsar's surface. At densities where a teaspoon of material weighs more than Mount Everest, the star's crust might briefly trap particles, preventing them from feeding the magnetosphere. Alternatively, the magnetic field lines themselves could twist into configurations that starve the polar regions of plasma, like kinks in a garden hose cutting off water flow. The pulsar's rotation doesn't stop, its engine keeps running, but the spark plugs fail to fire. The most unsettling part: these gaps don't follow predictable schedules. PSRB 1931+24 cycles between active and silent states roughly every 35 days, but other pulsars show entirely different patterns. Some switch off for years before suddenly roaring back to life, while others flicker erratically like a faulty neon sign. This unpredictability suggests the gaps aren't just passive voids, they're dynamic, evolving structures, shaped by feedback loops we're only beginning to map. Yet these enigmatic silences aren't just cosmic inconveniences. They're windows into the extreme physics governing neutron stars, revealing how even the most powerful magnetic fields can falter under the right conditions. Every time a pulsar's radio beacon winks out, it whispers a challenge to our models, and every time it reignites, it offers fresh clues about the invisible battle between matter and magnetism at the edge of reality. Some pulsars don't just pulse, they rage like cosmic tornadoes, their magnetospheres twisting into violent knots that unleash bursts of X-rays with terrifying unpredictability. These aren't the steady lighthouses of the cosmos we're used to. They're celestial storms where magnetic field lines tangle so tightly they snap like overwound rubber bands, flinging charged particles in chaotic eruptions. Take PSRJ 1846-0258, a neutron star that should have faded into obscurity after its supernova birth. Instead, it occasionally lights up with X-ray flares 100,000 times brighter than normal, as if something deep inside its magnetic machinery is short-circuiting. The secret lies in the star's magnetosphere, the invisible web of magnetic forces surrounding it. In most pulsars, these fields flow smoothly from pole to pole, guiding particles in orderly beams. But in these turbulent outliers, the field lines twist back on themselves like spaghetti in a whirlpool, storing energy until the system can't contain it anymore. When the tension finally breaks, the resulting magnetic reconnection isn't just a spark, it's a full-blown storm, accelerating electrons to near-light speeds and smashing them together with enough force to generate X-rays visible across the galaxy. What makes these cosmic tornadoes so erratic is their instability. Unlike the clockwork regularity of a typical pulsar's radio pulses, their X-ray outbursts follow no discernible schedule. One month, the star might flicker harmlessly. The next, it could unleash a flare powerful enough to ionize the interstellar medium for light years around. Astronomers compare it to predicting earthquakes. The stress builds invisibly until, without warning, the crust of reality itself seems to crack under the strain. Even more bizarre is how these twisted fields interact with the pulsar's superfluid interior. Beneath the solid crust, neutrons flow without friction, a quantum mechanical oddity that might amplify the magnetic chaos. Some theories suggest vortices in this superfluid could tangle the star's internal magnetic field like yarn in a blender, forcing it to erupt through the surface in unpredictable hotspots. The result, a star that doesn't just spin, it writhes, its entire magnetic skeleton convulsing under pressures we can barely simulate. Yet these magnetic maelstroms aren't just destructive. They're natural laboratories for studying how energy propagates through the universe's most extreme environments. Each burst encodes information about the invisible forces at work, like flashes of lightning illuminating the structure of a storm. By mapping their patterns, or lack thereof, scientists are piecing together a new understanding of how magnetism shapes the cosmos, one violent twist at a time. When a massive star explodes as a supernova, it doesn't just vanish. It leaves behind an expanding wreckage of gas and dust, threaded with magnetic fields powerful enough to sculpt chaos into eerie beauty. The Crab Nebula stands as one of the most spectacular examples, its ghostly tendrils glowing not from starlight, but from something far more exotic, charged particles spiraling at near-light speed through an invisible web of magnetism. This eerie light show, known as synchrotron radiation, turns the nebula into a cosmic particle accelerator, where electrons whip around magnetic field lines with such violence they emit a brilliant blue-white glow visible across 6,000 light-years. At first glance, the crab's filaments might look like random wisps, but their structure reveals an invisible order. The supernova's initial blast sent shockwaves rippling through interstellar space, compressing and twisting any pre-existing magnetic fields into intricate patterns. As the shock front plowed outward, it swept up charged particles, mostly electrons, accelerating them to relativistic speeds. These particles didn't just scatter, they became trapped, forced to spiral along the newly amplified field lines like cars on a twisted roller coaster track. With every twist and turn, the electrons shed energy in the form of synchrotron radiation, painting the nebula in wavelengths from radio waves to gamma rays. The result is a self-sustaining engine of light. The crab's central pulsar, a rapidly spinning neutron star, injects fresh particles into the nebula with every rotation, while the magnetic fields ensure they can't escape easily. Like a cosmic spiderweb, these fields trap and organize the chaos, channeling the energy into those hauntingly beautiful filaments. Without this magnetic scaffolding, the particles would simply dissipate into space and the nebula's glow would fade. Instead, we witness a dance of matter and magnetism that's lasted nearly 1,000 years and shows no signs of stopping. But the crab isn't just a pretty cosmic light bulb. Its magnetic fields act like a time capsule, preserving information about the original supernova's explosion mechanism. By studying the polarization of its light, how the waves align as they travel through the nebula's magnetized environment, astronomers have reconstructed the explosion's geometry, revealing it wasn't perfectly spherical. Instead, the dying star likely emitted jets or had an asymmetric collapse, imprinting its final moments onto the magnetic fields we see today. Perhaps most astonishing is the sheer energy involved. The crab's magnetic fields aren't just passively guiding particles, they're actively accelerating them, In some regions, electrons reach energies so extreme they could circle Earth equator 7 times in a single second. These particles don't just glow, they scream across the electromagnetic spectrum, creating a laboratory for studying high-energy physics on a scale no human machine could replicate. And the Crab Nebula is just one example. From Cassiopeia to the Vela remnant, supernova leftovers across the galaxy glow with the same synchrotron signature, proving that magnetism is as much a part of stellar death as fire and fury. These fields don't just illuminate the aftermath, they shape it, proving that even in destruction, the universe writes its laws in the language of invisible forces. Not all magnetars scream their power across the cosmos, some whisper it in bizarre, twisted signatures. Meet 4U0142+61, a magnetar that doesn't just crack under magnetic pressure but sings with seismic grooves etched into its X-ray emissions. While most of its kind blast space with erratic flares, this stellar oddity pulses with a strange rhythm, as if its very magnetic field has been sculpted into a cosmic vinyl record. The secret lies in its helical magnetic field, a structure so warped it resembles a barber's pole of invisible force. Unlike the relatively orderly fields of typical magnetars, 4U0142+61's magnetic lines spiral around its axis like coiled springs, storing energy in their twists. When starquakes ripple through its crust, these helices vibrate at precise frequencies, imprinting faint grooves onto the star's X-ray spectrum. To astronomers, these spectral lines aren't just noise, they're a Rosetta Stone for decoding the magnetar's hidden geometry. What causes this helical madness? One theory points to the star's birth. Most magnetars form when collapsing stars preserve their progenitor's magnetic field, amplifying it through compression. But if the dying star was exceptionally turbulent, perhaps locked in a binary dance or riddled with asymmetrical current, its field might have twisted like a tangled slinky as it collapsed. The result, a neutron star born with magnetism that doesn't just point at corkscrews. These grooves aren't static. Observations reveal they shift subtly after starquakes, suggesting the magnetar's crust isn't just cracking, it's rearranging the star's entire magnetic architecture. Picture a frozen lake fracturing underfoot, except the ice is a kilometer-thick lattice of iron nuclei, and the cracks realign magnetic fields capable of atomizing matter. Every seismic event tweaks the helices, altering how particles accelerate along them, and thus changing the pitch of the grooves. The implications stretch far beyond one weird magnetar. If helical fields exist here, they might explain why some magnetars flicker unpredictably while others, like 4U0142+61, pulse with eerie precision. It's a reminder that in the universe's most extreme laboratories, even magnetism, a force we think we understand, can twist into shapes that defy our textbooks. And sometimes the most profound discoveries don't come from the loudest explosions, but from the faintest grooves in the data. If you could take a step near a magnetar's crushing magnetic field, you wouldn't just feel your atoms stretch, you might accidentally walk into a time warp. According to Einstein's theory of general relativity, anything with enough energy, including magnetism, can bend spacetime itself, and magnetars take this to the extreme, with fields so intense they don't just twist light, they could twist the fabric of time into knots. The math gets wild here. Under certain conditions, these fields might theoretically create what physicists call closed time-like curves, loops in spacetime where an object could, in theory, return to its own past. Think of it like a cosmic Möbius strip. Normally, time flows in one direction, an arrow we can't reverse. But near a magnetar's unimaginable magnetism, the rules get fuzzy. The field's energy warps spacetime so severely that the future and past could curve back on themselves, like a hallway that somehow loops into its own entrance. This isn't science fiction, it's a real, if speculative, consequence of Einstein's equations. In simulations, when a magnetic field reaches magnetar-level intensities, it generates space-time distortions that could, mathematically at least, permit time travel. There's a catch, of course. You'd need to survive the Magnetar's other deadly traits first, like the gravitational tides that would spaghettify your body or the X-ray bursts that vaporize matter. But let's say you had some indestructible probe. Even then, the time loops created would be microscopic, lasting fractions of a second. You couldn't hop back to prevent historical events, just take a fleeting peek at what happened a moment ago. It's less Back to the Future and more Groundhog Day on Fast Forward. The real surprise, this idea isn't purely hypothetical. Some physicists argue that magnetars might already be creating these closed time-like curves, just on quantum scales. Particles caught in the field could briefly revisit their own past states before continuing forward, like a cosmic echo. If true, it would mean time travel isn't confined to wormholes or black holes. The universe might be stitching together tiny time loops every time a magnetar's crust quakes, offering glimpses into physics we've only dreamt of testing in labs. Of course, no one's claiming this proves time travel is possible yet, but the fact that magnetism, a force we harness in everyday tech, could under extreme conditions twist time itself. That's a reminder of how much we still have to learn about the universe's most ordinary-seeming forces. And if there's one place to look for answers, it's in the violent, time-warping hearts of these cosmic magnets. Most magnetars spin slowly, their rotation weighed down by the sheer might of their magnetic fields, but J1818.0-1607 laughs at the rules. Clocked at 1.4 rotations per second, this cosmic rebel is the fastest spinning magnetar ever discovered, whirling faster than a kitchen blender despite being shackled by magnetic forces strong enough to rip molecules apart. Its existence isn't just unusual, it's a direct challenge to everything we thought we knew about how these extreme objects form. Normally, magnetars are stellar sluggards. Their ultra-strong magnetic fields act like cosmic anchors, sapping rotational energy through a process called magnetic braking. Over millennia, even the most rapidly spinning neutron stars should grind to a crawl under this relentless drag. Yet J1818.0-1607 defies this fate, spinning with the vigor of a much younger, less magnetically burdened pulsar. The discrepancy is staggering, like finding a freight train barreling down the tracks at Formula One speeds. So how did this oddball escape the brakes? One theory suggests it's a newborn by cosmic standards, forming so recently that it hasn't had time to slow down. Estimates place its age at just 500 years, barely a blink in astronomical terms. Supporting this, astronomers found debris around it consistent with a recent supernova, as if the star's explosive birth hasn't even finished settling. But youth alone doesn't explain its speed. Even freshly minted magnetars shouldn't spin this fast unless their progenitor stars were already rotating furiously before collapse, packing extra angular momentum into their cores like a spinning figure skater pulling in their arms. Another possibility, this magnetar might have stolen its speed. Some models propose it once orbited a companion star, siphoning off gas that transferred angular momentum like a cosmic slingshot. The stolen material could have acted as a temporary power-up, counteracting the magnetic drag just long enough to keep its rotation defiantly brisk. Yet no companion remains today, leaving astronomers to wonder, was it obliterated in the supernova, or did the magnetar's gravity fling it into interstellar space during their chaotic dance? What's undeniable is that J1818.0-1607 isn't just spinning fast, it's also alarmingly active. Unlike older magnetars that settle into occasional tantrums, this one crackles with X-ray bursts and radio emissions, as if its hurried rotation is stirring its magnetic field into a frenzy. Every pulse carries clues about its internal structure, hinting at a turbulent interior where superconductivity and quantum weirdness might be propping up its speed against all odds. The implications ripple far beyond this one oddity. If magnetars can retain or regain rapid rotation, even briefly, it reshapes our understanding of their life cycles. Perhaps there's an entire population of young, fast-spinning magnetars we've missed, their speed hiding them in plain sight among more ordinary pulsars. Or maybe J1818.0-1607 is a rare hybrid, a magnetar with the soul of a pulsar, straddling two extremes in a way no theory predicted. One thing's certain, this cosmic speed demon proves that even the universe's most rigid rules have exceptions. And when it comes to magnetism, rotation, and the laws of physics, sometimes the outliers teach us more than the textbooks ever could. Dark matter might be invisible, but its fingerprints are everywhere, bending light around galaxies, sculpting the cosmic web, and holding clusters together with its gravitational glue. Yet for all its influence, one question haunts scientists. Could this mysterious substance be tangled up with the universe's primordial magnetic fields? The idea sounds like science fiction, but some theorists argue these invisible forces might have shaped each other in ways we're only beginning to uncover. Picture the early universe, a seething plasma where charged particles zip through space, generating weak but pervasive magnetic fields. These primordial fields, stretching across light years, could have interacted with dark matter's gravitational pull in subtle yet profound ways. One provocative theory suggests that certain types of dark matter particles might carry a tiny electromagnetic charge, not enough to glow like normal matter, but just enough to feel the tug of magnetic fields. If true, these particles wouldn't just drift aimlessly, they'd be herded by magnetic forces, clustering in ways that pure gravity alone couldn't explain. The evidence might lie in the cosmic structures we see today. Galaxies often spin faster than their visible matter should allow a classic sign of dark matter's presence. But some galaxies also show oddly coherent magnetic fields spanning thousands of light years with strengths that don't quite match predictions. Could these fields be relics of an ancient partnership between magnetism and dark matter, woven together during the universe's formative years? Simulations hint that primordial fields might have guided dark matter into the filamentary cosmic web we observe, acting as invisible scaffolding for the largest structures in existence. Even more tantalizing is the role these fields might play in solving the missing satellites problem. Dwarf galaxies, the tiny, dark matter-rich satellites orbiting larger galaxies, are far fewer than simulations predict. But if primordial magnetism subtly altered how dark matter clumped in the early universe, it could explain the discrepancy. Some models show magnetic pressure preventing small dark matter halos from collapsing, leaving fewer survivors to become dwarf galaxies today. Of course, not all dark matter needs magnetism to exist. The majority might still be utterly indifferent to electromagnetic forces. But if even a fraction interacts with these fields, it would revolutionize our understanding of both dark matter and cosmic magnetism. Future telescopes, like the Square Kilometre Array, could hunt for telltale distortions in the polarization of ancient light, subtle warps that might reveal dark matter's magnetic whispers from the dawn of time. Until then, the connection remains a captivating mystery, one that reminds us how much of the universe's story is written in forces we can't see, but whose influence echoes across billions of years. And if magnetism and dark matter truly dance together in the cosmic dark, their partnership might be the key to unlocking the universe's deepest secrets. Black holes are supposed to be the simplest objects in the universe according to the no-hair theorem. They can be described with just three parameters: mass, spin, and charge. Anything else, their history, composition, or magnetic properties, should vanish beyond the event horizon, leaving them bald, so to speak. But recent simulations have thrown a wrench into this elegant idea, suggesting black holes might actually sport wild, unkempt magnetic hair that defies our clean mathematical models. This isn't just a cosmic bad hair day, it's a potential revolution in how we understand these gravitational monsters. The chaos starts in the accretion disk, that swirling maelstrom of superheated gas and plasma circling a black hole's maw. As particles collide and ionize, they generate electric currents, which in turn produce magnetic fields. Normally, these fields would fade into the black hole's interior, never to be seen again. But advanced simulations now show that under certain conditions, particularly when the black hole spins at breakneck speeds, these fields can get frozen into the space-time just outside the event horizon. Like strands of cosmic hair, they linger, twisting and tangling in ways that contradict the no-hair theorem's minimalist vision. What's stranger is how this hair behaves. Unlike the smooth, predictable fields around magnets or stars, these structures are chaotic, forming loops and braids that shift unpredictably. Some simulations even suggest the fields might self-sustain, with plasma currents reinforcing the magnetism in a feedback loop that refuses to die. The result, a black hole that isn't just a featureless pit but a dynamic object with a complex magnetic personality, one that could influence how it feeds, spins, and even how it interacts with other black holes during mergers. The implications ripple far beyond theory. If black holes really do have magnetic hair, it could explain some baffling observations, like why certain jets of particles shoot out with such precision. These fields might act like cosmic railguns, channeling and collimating the jets in ways that pure gravity can't. It could also mean that black holes carry hidden memories of their past encoded not in their mass or spin, but in the tangled magnetic patterns clinging to their surfaces. Of course, not everyone's convinced. Critics argue that these simulations might be missing key physics, like quantum effects near the event horizon. Others point out that even if magnetic hair exists, it might be too faint to detect. But the mere possibility shakes the foundations of black hole physics, proving that even the universe's simplest objects might be far more complicated and far more fascinating than we ever imagined. A magnetar passing within a few 100 million miles of Earth would unleash a silent apocalypse. No fireballs, no quakes, just an invisible storm of magnetism rewriting the rules of physics on our planet. First, the auroras. Forget the gentle green curtains of the Arctic. These would be global, blinding displays stretching from pole to pole as the magnetar's field violently interacts with Earth's own magnetic shield. The sky would ignite in ultraviolet and X-ray flashes, visible even at noon as the atmosphere itself becomes a fluorescent lamp under particle bombardment. But this light show comes at a cost. Every satellite in orbit would be fried within hours, their circuits overloaded by induced currents as the magnetar's field sweeps across them like an electromagnetic tsunami. GPS, communications, even the International Space Station systems, all reduced to dead metal husks tumbling through space. The real danger lurks in the ground. Power grids designed to handle ordinary solar storms would buckle under currents 1,000 times stronger. Transformers would explode like popcorn, plunging continents into darkness that could last years, not from lack of fuel, but from the impossibility of manufacturing replacements fast enough. Buried cables would act as accidental antennas, channeling destructive energy into hospitals, data centers, and nuclear plants. Imagine every electronic device simultaneously sparking, from pacemakers to dam control systems, as the magnetar's field turns the planet into a giant Faraday cage gone haywire. Most chilling of all, the atmosphere might start leaking into space. While Earth's magnetic field usually protects our air from solar wind erosion, a close magnetar encounter could rip open temporary gaps in that shield. Charged particles in the upper atmosphere, normally held in place by magnetism, would get accelerated to escape velocity, dragging neutral oxygen and nitrogen molecules with them in a process called ion outflow. Over months, this could strip away significant atmospheric pressure, thinning the air we breathe and triggering a slow-motion climate catastrophe. The same phenomenon turned Mars from a wet world to a frozen desert over billions of years. but a magnetar might jumpstart that process on human timescales. Yet amidst the chaos, there's a bizarre silver lining. The magnetar's field could briefly make the impossible possible. Quantum effects normally confined to lab experiments might manifest macroscopically superconductivity in everyday materials, metals floating at room temperature, even subtle time dilation measurable with household clocks. For a fleeting moment, Earth would become a playground of extreme physics, revealing secrets about magnetism, matter, and space-time that we could never replicate artificially. Then, as the magnetar recedes into the void, we'd be left with a transformed world, one where the night sky no longer holds just beauty, but a visceral reminder of how fragile our place in the cosmos truly is. The swirling chaos of a young star's protoplanetary disk might look like pure anarchy, but hidden within that turbulence lies an invisible architect magnetism. Take H.L. Tauri, a stellar toddler barely 1,000,000 years old, whose dust-filled disk has become a cosmic Rosetta Stone for understanding planet formation. At first glance, the disk's concentric gaps seem carved by newborn planets, but the real sculptor might be magnetic fields, weaving through the gas like cosmic puppet strings. These forces don't just passively watch the chaos, they actively funnel material into the paths of growing worlds, turning a star's leftovers into the building blocks of solar systems. Imagine a celestial whirlpool where every particle is a magnetized speck of dust. As the disk rotates, charged particles spiral along magnetic field lines, creating currents that shape the flow of material. In H.L. Tauri's case, these fields act like invisible traffic cops, steering dust and gas into orderly lanes that eventually coalesce into planets. The stunning ALMA telescope images of its gaps aren't just empty space, they're evidence of magnetic barriers, regions where field lines push matter away, creating the illusion of rings. It's as if the disk is breathing, exhaling material from some zones while inhaling it into others, all under magnetism's silent command. What's fascinating is how these fields solve the meter-size problem, a long-standing puzzle in planet formation. Tiny dust grains can stick together through static electricity, but once they grow to pebble size, collisions tend to shatter them. Magnetic fields offer a way out. By aligning particles like beads on a string, they help clumps grow without destructive crashes. Simulations show magnetized turbulence can even create pressure traps, regions where material accumulates like snowdrifts, shielded from the disk's violent whirl. These traps become planetary nurseries where baby planets bulk up safely before migrating to their final orbits. The proof isn't just theoretical. Polarized light observations reveal H.L. Tauri's disk is threaded with magnetic structures, their telltale imprints visible in the way dust grains align. Some regions show field lines twisted like corkscrews, likely from the star's rotation warping the disk's inner layers. Others exhibit radial patterns, where magnetism channels material directly onto the star or its fledgling planets. This isn't just a snapshot, it's a dynamic blueprint showing how magnetism bridges the gap between stardust and worlds. Yet the story doesn't end there. These same magnetic fields might also trigger the final act of planet birth. As young gas giants form, their gravity can disrupt the disk's field lines, sparking eruptions of plasma called magnetic reconnection events. These cosmic short circuits heat nearby gas, potentially explaining why some disks glow unexpectedly in X-rays. The energy released could even kickstart chemistry, forging complex molecules that later seed planets with the ingredients for life. H.L. Tauri's gaps are more than pretty pictures, they're windows into a process that built our own solar system. 4.6 billion years ago, similar magnetic forces likely guided Earth's formation, deciding which particles became continents and which vanished into the sun. Today, as we study these distant disks, we're not just watching planets being born, we're unraveling the invisible forces that made our cosmic home possible. And if magnetism could sculpt worlds here, imagine what else it's shaping in the unseen corners of the universe. galaxy clusters don't just contain magnetic fields, they weave them into structures so vast they could swallow the Milky Way whole. Take the Coma cluster, a cosmic titan over 300 million light-years away, where tangled magnetic threads stretch across millions of light-years like the universe's largest spiderweb. These aren't the orderly fields of stars or planets. They're chaotic tapestries forged in collisions between galaxies, where entire spiral arms rip apart and merge in gravitational chaos. The result, a sprawling labyrinth of magnetism, its tendrils glowing faintly with synchrotron radiation as they guide cosmic rays through intergalactic space. What's astonishing isn't just the scale, it's how these fields persist. Galaxy clusters are battlegrounds filled with superheated gas and dark matter, where turbulence should tear magnetic structures apart. Yet observations reveal the opposite. The Coma cluster's fields are shockingly stable, their energy replenished by the very violence that seems poised to destroy them. When galaxies collide, their interstellar magnetic fields don't vanish, they stretch and reconnect, merging into larger, more complex configurations. It's like two combative painters blending their canvases, creating something neither could achieve alone. The charged particles caught in these collisions get whipped to relativistic speeds, amplifying the fields further in a self-sustaining feedback loop. The proof lies in the radio waves. As electrons spiral along the cluster's magnetic highways, they emit synchrotron radiation, painting the otherwise invisible fields in shades of radio light. Astronomers using arrays like the Very Large Array have mapped these emissions, revealing filamentary structures that defy expectations. Some threads follow the trails of galaxies stripped of their gas during close encounters, while others form vast bridges between colliding subclusters, magnetic umbilical cords tethering giants together. But the real surprise, these megaparsec-scale fields might regulate the cluster's entire ecosystem. By channeling cosmic rays and heating intergalactic gas, they prevent runaway cooling that would otherwise trigger catastrophic star formation. Without this magnetic scaffolding, galaxy clusters could become overcooked stellar nurseries, burning through their fuel in frenzied bursts. Instead, the fields act like cosmic thermostats, maintaining a delicate balance between chaos and order. Perhaps most mind-bending is the timescale. These magnetic behemoths take billions of years to form, outliving the galaxies that birthed them. They're not just relics of past collisions, they're living structures evolving as new mergers inject fresh energy. In a sense, they're the universe's way of turning destruction into art, weaving chaos into patterns that might one day seed the next generation of cosmic giants. The final frontier in our exploration of cosmic magnetism isn't in distant galaxies, it's unfolding right now in mission control rooms and scientific workshops, where engineers are preparing spacecraft to decode the universe's most extreme magnetic secrets. Leading the charge is the European Space Agency's LISA mission, a ground-breaking endeavor slated to launch in the mid-2030s. Unlike traditional telescopes, LISA won't rely on light, it'll hunt for gravitational waves rippling from cataclysmic events involving magnetars and black holes. Imagine detecting the space-time shudders unleashed when a magnetar's crust fractures under magnetic strain, or capturing the resonant hum of a black hole's jet as it twists the fabric of reality. These signals, invisible to conventional instruments, could reveal how magnetism warps spacetime itself, offering clues about phenomena we've only theorized, like quantum gravity or extra dimensions. Meanwhile, NASA IXP telescope is already revolutionizing our view from orbit. Launched in late 2021, this X-ray polarimetry pioneer doesn't just observe cosmic magnets, it dissects the very orientation of their emissions. Ordinary telescopes see magnetars as blazing dots, but IXP maps the intricate swirls of polarized X-rays spiraling from their magnetic poles. This is like swapping a blurry black and white photo for a high-definition 3D model, revealing how particles accelerate along twisted field lines during starquakes. Early targets include the bizarre anti-magnetar 4U0142+61, whose helical magnetic grooves might finally be decoded. Its findings could settle decades-old debates, like whether magnetars power their flares through crustal snaps or deeper magnetic upheavals. But the future doesn't stop there. Proposed missions like NASA's Astrobe X aim to take X-ray scrutiny even further, with detectors sensitive enough to catch millisecond fluctuations in magnetar outbursts. Picture watching a high-speed film of a neutron star's magnetic reconnection, frame by frame. And on the horizon looms the square-kilometer array, a radio telescope network so vast it could map galactic magnetic fields in unprecedented detail, tracing their influence from stellar nurseries to supernova remnants. These missions share a common goal: to peel back the layers of cosmic magnetism, exposing its role in everything from particle acceleration to spacetime itself. With every launch and discovery, we're not just building better tools, we're rewriting the story of how invisible forces shape the visible universe. And as these projects unfold, one truth becomes clear: the golden age of magnetic exploration has only just begun. From magnetars shredding atoms with their quadrillion Gauss fields to black holes sprouting chaotic magnetic hair, we've journeyed through a universe sculpted by invisible, irresistible forces. These aren't just cosmic curiosities, they're the architects of reality, bending light, warping space-time, and even rewriting the rules of time itself. Imagine a neutron star's crust cracking under magnetic strain, unleashing enough energy to outshine galaxies, or supermassive black holes weaving magnetic filaments so vast they could tether galaxies together. These extremes aren't anomalies, they're the universe's way of pushing the limits of physics, showing us how magnetism shapes everything from the birth of stars to the death of galaxies. Think back to the Crab Nebula, its ghostly tendrils glowing with synchrotron light as particles spiral through magnetic labyrinths, or the helical grooves of Magnetar 4U0142+61, singing seismic melodies into the void. Even Earth's humble field, a whisper compared to these titans, shields us from solar storms and paints our skies with auroras, proof that magnetism's touch is both destructive and nurturing. So next time you hold a fridge magnet, remember, it's a tiny echo of the cosmos' most extreme forces. Which fact left you awestruck? Was it the time-warping fields of magnetars, the galactic scale webs of the Coma cluster, or something else? Drop your favorites in the comments and let us know what cosmic mysteries we should explore next. The universe's magnetic story is far from over, and every discovery pulls us deeper into its invisible, irresistible